Okay, so what we're going to be focusing on in this lesson is factoring the final two types of problems that we've not yet done, and these are linked to some special products that we found in section 9.3, and so there's a couple of examples of them below here, and so what I'm going to do is quickly take you through the distribution of these, and that way we'll be able to identify the pattern in the distribution, and this in turn will give us some insights into what procedure we need to use for factoring, because of course distribution and factoring are reverse processes. And so what we'll do is distribute them out, and so over here we're going to have x times x, which is going to give us x squared. X times plus 5 will give us our plus 5x, minus 5 times x, minus 5x, and minus 5 times plus 5, minus 25. If we identify our like terms and add and subtract, our final simplified product yields x squared minus 25, and what you'll notice is that those two middle terms cancel each other out. So this is an example in factoring terms of something called a difference of two squares. It is a difference of two squares because it has the minus sign for the difference. X squared is a perfect square, and 25 is a perfect square as well. Okay, so let's move to x minus 4 all squared. So as we know, this should be written out as x minus 4 multiplied by x minus 4, just as x squared is x times x. So if we square an entire parenthesis, we must write out x minus 4 times x minus 4, and this is a binomial. There are two terms in each parenthesis, so we must not make the mistake of simply squaring each term. And so you'll see when we use our distribution that we in fact end up with a trinomial as our answer. So we have x times x to give us x squared, x times minus 4 gives us minus 4x, minus 4 times x gives us another minus 4x, and minus 4 times minus 4 plus 16. Then what we're going to do is add and subtract our like terms, and our final product x squared minus 8x plus 16, and so this is known as a perfect square trinomial. Perfect square trinomial because it produces a trinomial when you've completed the distribution and simplification process, but it came from a perfect square, the squaring of a binomial. And so what the focus of today's lesson is going to be starting with a difference of two squares, or with a perfect square trinomial, and working back to the factored form, since, as I mentioned before, factoring and distribution are opposite or reverse processes. Okay, so let's get straight into some examples. So what we have now is a series of examples which each contain two terms, and so when we have two terms, what we're focusing on is the possibility, of course, of the difference of two squares. And so obviously we have a minus sign in there, we have x squared, and we have 9. Both of those are perfect squares, and so from a factoring point of view, you could view this as x squared plus 0x minus 9, and look for the combination of factors of 9 and x squared, which are going to give you a middle term that cancels out. So this could be viewed in the standard form of a trinomial. And so if we do it that way, we look to get the x squared is x and x. To get the 9, we could use 9 and 1 as our factors, or we could use 3 and 3. And we have a minus, so we know that we have 1 plus and 1 minus. Of course, in this case, since we have no middle term, were you to cross multiply x by 9 to give you 9x and x by 1 to give you 1x, whether we added or subtracted those, we could not get to 0, and so we quickly see that 9 and 1 is not a combination that will work. What we can see, however, is that x by 3 is going to give us 3x, x by 3 is going to give us 3x, and as long as we ensure one of them is a plus and one of them is a minus, this will allow us to eliminate our middle term, and at the same time get x squared for our first term and minus 9 for our last term, and here we have a successful factoring of the difference of two squares. Okay, so again, it's all about the pattern. Once you can recognize it as a difference of two squares, we can in fact, in these cases, go directly to an answer. And so it factors, even though it is a binomial, two terms separated by a minus sign, even though it's a binomial, it factors as a trinomial, namely a binomial times a binomial, which typically produces a trinomial when we distribute. But in this case, we have an exception to that rule. And so to get our x squared, x and x, to get 16, of course, we have options for 8 and 2, 16 and 1, 4 and 4. But because we have no middle term, what we want is the combination of factors which are the same, one with a minus, one with a plus, and that will guarantee that we get 0x as our middle term, and it will also guarantee that we get minus 16 as our final term. So when we factor x squared minus 16, x plus 4, x minus 4. Okay. The purpose of example C is to show you an exception to the factoring rule. And so if we use the same approach as we've used in the previous two examples, open a set of parentheses. To get our x squared term, we need x and x. Once again, we have no middle term. And so to ensure that we can get a middle term that cancels out, we want to use the factors for 4, not of 4 and 1, but instead of 2 and 2. And what we're going to see here is an instance where we cannot factor, and the problem is going to be the sign. Because if we were to use minus 2 and minus 2, which is one of the ways of ensuring we get plus 4, of course, if we distribute that out, we're going to get x squared minus 2x minus 2x plus 4. We will get our plus 4, we will get our x squared, but you are going to get a middle term of minus 4x, and we don't have a middle term of minus 4x. Were we to use a plus and a plus, we would have a similar issue. We would still get the first and the last term, but once again we would get a middle term. And finally, were we to use 1 plus and 1 minus, we would get our first term, and we would get our middle terms to cancel out, so we would get x squared minus 2x plus 2x, and those would cancel out, which works out, but the problem is we would then end up with minus 4, not plus 4. And so basically what you need to conclude from all of this is that if we are given the sum of two squares, the conclusion from a factoring point of view is that it cannot be factored. Okay, and if we look at example D, we appear to have a question which is not factorable. Again, the reason for this is that 2 and 50 are not perfect squares, but this is an example of a combined factoring sum, and so what we're going to do to begin with is remove a GCF. And so in this case, if we were to remove 2, we would be left with x squared minus 25, and if we look inside the parentheses, we should be able to recognize that we have now, after factoring out the GCF, left ourselves with a perfect square for the first and last terms, and we have a difference, and so we would be able to go on and factor the terms inside as x and x, 5 and 5, 1 plus and 1 minus, to ensure, of course, that we don't get a middle term. And this would be the final solution in factored form to the expression 2x squared minus 50. Okay, so what we'll do is jump ahead to some more examples. These focus on perfect square trinomials, and so the previous examples were a difference of two squares. Now what we're going to focus on is the perfect square trinomial. We can factor these just like we would factor any other trinomial. Factors of the first term, x and x. Factors of the last term are going to be 3 and 3, 9 and 1. If we look over here, we see that the signs are going to be the same, and we will have two minuses, so that makes our life a little bit simpler. And now what we need to do is multiply to see which pair of factors is going to yield our middle term. In this case, we'll see minus 3x will leave us with the minus 6x that we want. And what you're going to see is our approach is exactly the same as any other trinomial. It's just our final result is a little bit special. And so what we end up with is x minus 3 times x minus 3, which could be written as x minus 3 all squared. And so again, the fact that it could be written like this, we don't really need to change our approach with a perfect square trinomial. That said, if we recognize the pattern, we can get to a solution much faster with much less work. Okay, and so again, I'll just take you through the motions exactly as if it were a regular trinomial, but again, once you spot the pattern, you'll see that you can get straight to an answer. So factors of x squared, x and x, factors of 1, in this case only 1 and 1, same signs, both positive, and so all we'd need to do is just make sure that we can get our middle term. So we'll have plus 1x, which will give us plus 2x, and we can go straight to our factored solution at this point, x plus 1 times x plus 1, or you may write it as x plus 1 all squared. Alright, so in G and H, we've got the same kinds of problems, slightly different in the sense, however, now that we have a lead term with a coefficient other than 1, and so in this case what we should be considering is possibilities for 3x and 3x. For our last term we have 1 and 1, and I'm going to write just on the end here the other possibility to get 9x squared, which will be 9x and x. Signs are the same, in this case both minuses, and so what we could do now is test our 3x factors, 3x and 3x with 1 and 1, or we could test 9x and x with 1 and 1. And so what you'll see fairly quickly once you get the hang of this is that these are the factors we're interested in, minus 3x to give us minus 6x, and we can go straight to our answer, 3x minus 1 all squared. Okay, same kind of problem, slightly more complicated because we have choices for the first and last, and again, in this lesson, we're fairly safe to assume that it's going to be a perfect square trinomial. On an assessment, you wouldn't know that for sure. We do know that 4x squared could be square rooted as 2x times 2x, 9 could be written as 3 times 3, and so that's how we know that there's the possibility that it's a perfect square trinomial. And so once you get the hang of this, you could start off by testing that quickly to see if it worked, and if it didn't, we could move to testing other factors. And so we'll start by just testing that 2x and 2x, 3 and 3, same signs, both plus, and so that'll give us a plus 6x, which will give us plus 12x and allow us to go straight to our answer. Again, if that hadn't worked, then we would have gone ahead to consider other possibilities, 4x and 1x, 9 and 1 as the other possible factors, and then we might have factored just as we did in the previous lessons. Okay, so at this point what you need to do is pause the video, go ahead and give examples I and J a try, and then restart the video and I'll write up solutions for those and you can check how you did. So go ahead and try those now, pause the video and try those. Okay, and so we're back. What I'm going to do now is just write up very quickly some solutions to the last two. What you should see here is we don't have perfect squares in the first and last term. If we factor out the 3, however, we will obtain the following, and inside there we have a perfect square trinomial. That's a perfect square, that's a perfect square, and the factors will combine to give us plus 2xy, and so we can go directly to our answer, leave 3 outside. X signs are the same, they are both plus. X plus y times x plus y will give us the x squared plus 2xy plus y squared with 3 outside. Similarly, we're going to factor out our minus 3, x squared minus 12x plus 36. Final answer, x minus 6 all squared.